Looks good. All right. So 3, 2, 1. We're live.
Greetings, Eigen people.
Greetings, Eigen they, thems, Eigen she,
Eigen she, her, him.
she, hers, hims. Thank you. We're inclusive.
Canceled.
No, we're
Once
inclusive. I fucked up pronouns, so I'm canceled. Nah, we're an inclusive podcast, and today we're including our friend Joe.
Yes, indeed.
Yes.
Many of you true fans out there may remember Joe from some of the older episodes that we did with Eric Weinstein, and also, who else did we do, Joe?
Yeah, Eric was there. Yeah. Joe Rogan was there.
It's a great time, right?
I don't even remember who else we did.
We do all the physicists, so I think maybe we did Brian Green or something. Or, no,
Brian
we didn't do
Green.
Brian.
Yeah, we
did we do Brian Green? Okay.
No, I don't think that was me.
I think it might have just been us two.
Sure.
Maybe we did Sean Carroll.
Probably. Let's say yes.
Okay, whatever.
I don't even remember.
It's too long ago for Joe to remember this stuff,
yes.
and must as well.
Be a yes man on the podcast.
But yeah.
How long ago was that, the Eric?
Too long ago.
Yeah.
You know what's crazy was Eric actually told me he watched that podcast.
Oh, no.
No.
I was like, holy shit, you actually watched our podcast? He's like, yeah. He said it was really weird watching people talk about you. And I was like, oh, I hope we said nice things. He's like, oh, yeah, you guys were great.
Did he have his pants? Did he have his pants down? I want to know. Eric, if you think we're sexy, let us drop a sexy in the comments below.
No, don't say that. I'm trying to get Eric to actually like us.
No, Eric, I think he'll appreciate the comedy we bring to the table. I think
probably. Yeah, Eric's got a sense of humor.
Yeah, he does. He's a funny guy.
Yeah.
But no, well, like last time we were fumbling the show because we're like, we know nothing about astrophysics.
Yeah. Literally, the last episode, we were we do like nothing on astrophysics. I think we did maybe one episode with Sahana on Astro, but that was
she
still
does astronomy, right?
Yeah. But it was kind of informative, I think. But still, I think we need to do more Astro stuff.
For sure,
right?
Yeah.
We should,
I mean, it's one of the 3 fields.
That
we discovered.
I can't believe it's only 3. That's so weird. Because we were saying this the other day, Joe. Do you? Maybe you can remember or help us out too, because we were thinking there's only 3 fields of physics really. Condensed matter, nuclear, high energy. We'll kind of couple those two, and then Astro. Is that it for real?
Yeah, I mean, I'm not sure about combining nuke and high energy, but other than that, yeah, I guess so.
Okay. Yeah, that's fair too, because they have a designation for a reason. Nuclear and high energy are separate in the physics world, but
they're like particle physics either way to me.
Yeah, but they use different models, right? So nuclear people use specific models, and then high energy people use specific
it's like
models.
Relativistic and non-relativistic.
Yeah,
right?
Yeah. I think it's more than that, because I think the models are like still like they're still like approximations for certain regimes. So like nuclear people will use like 3 different models depending on what they're doing.
Gotcha.
It's kind of disconnected in some ways.
Gotcha.
So I guess it's fair.
So is non-relativistic, since you're in astrophysics, you guys talk about non-relativistic stuff, relativistic stuff a lot, I imagine.
Sure, yeah.
Yeah, because I imagine like the non-relativistic stuff is the sexy stuff. No, the relativistic stuff is the sexy stuff.
Yeah, but the non-relativistic is probably easier stuff.
Yeah.
I mean, I guess. Like if you're dealing with relativity, I mean, you're in for a headache, right?
All these
coefficients and stuff. For the layman, GR is very relevant in Astro, because really the thing is GR has to do with, and that's general relativity, has to do with the curvature of space-time.
Sure.
So when you have more massive objects, you get more curving of space. So
yeah, and most of the research I've seen, though, GR, you could kind of ignore it, right?
Oh, really?
Yeah, I mean, if you want to be more accurate, you'll include like GR effects.
Oh, so the corrections are small, basically, or what?
It obviously depends on what you're looking at, right? But
like supermassive black holes, you can.
Yeah, of course. Yeah.
Okay.
If you're interested in black holes, GR is probably in your wheelhouse.
So you better love tensors and Christoffel bullshit.
Yeah, I literally had a dream last night about somebody saying tensors to calculating some tensor thing. I was like, why am I dreaming about tensors?
Nerd.
Yeah. And not even like I was admiring somebody who was doing the work. I was like, this is very good work. I don't know what the hell I was thinking.
So Juan loves tensors.
Quarantine dreams. It's just been so strange. But yeah, man, I know I know you brought a book with you, actually.
What have
you been reading lately?
If you want to talk about that, I mean, so I guess I'll just plug my podcast, right?
For sure.
Been getting back into that. The book I have with me is called Conscious. It's by Annika Harris.
More free advertising.
Well, it's because my podcast, Beyond the Physics, right? We're trying to start up another series, a book club.
Oh,
nice, dude.
Right. So if you're interested in checking out our podcast and you want to check out the book club, go ahead and this is your reading assignment.
Hell yeah.
Conscious.
I'm gonna have to
Guys,
ask you
check
that.
out
I'll look. I'm a reader, bro. I'll come and read whatever and then come and talk about it.
Right. So we chose this book on purpose because we had our podcast together, right, about objective morality, and we hope to make it like a more like overarching series about like what is consciousness, how that could possibly relate to physics and stuff like that. And so this would be a natural jumping off point for a book club, and it's very small, right? It's like 100 pages. If you took a day out of your week, you could probably finish it.
Yeah, true.
Cool,
Right.
man. Yeah.
So we're planning on having a conversation about that soon. So if you guys are interested,
Yeah, we definitely have a follow-up to that. Because I'm not sure how our conversation ended.
Oh, with
me
the
and Terence had a
objective morality?
discussion about
Oh,
objective
didn't we
morality.
like backpedal our
We did.
original? Because I think we settled on objective morality
at the
with
end of
Joe
your
and
show.
Irene. Yeah, at the end of their show. But then recently we talked about it again, and we came back full circle to subjective morality. But I don't know. I don't remember the argument now.
Yeah, I don't either. So we're just
We'll
gonna
have to, maybe we'll do a part 2 or something.
that's a big old can of worms.
So once I read this book, we'll dissect
Yeah.
this further. But
Yeah. So, anyways, check it out and keep an eye out for that stuff. But
Cool, man.
check
guys,
out Joe's podcast too.
Yes, and I think Joe, is it still on just like Apple, Spotify?
it's Apple, Spotify, iHeartRadio is interestingly the most popular. It's on everything pretty much.
Okay, yeah.
Overcast, whatever.
Yeah. You just send out the RSS feed, and then it's all taken care of.
Yeah.
But you guys are not going to do video podcast.
No, we've been doing audio.
Okay, cool.
Right, so
guys, make sure you check out all those platforms, whatever one you're comfortable with, and then you'll find Joe there.
Yeah. So we've been making new episodes. I don't know if you've checked out any of them recently, but
No, I didn't know you guys were starting back up.
yeah, probably since our long break, we've put out like 4 more or something.
Oh,
And
okay.
then-
I noticed you were on Twitter a couple times.
Yeah, I retweeted your stuff. You saw.
Yeah. I was like, oh, okay, Joe's on Twitter. I don't know. I didn't know you guys were actually starting the podcast back though.
Yeah, so check
I'll
it
have
out.
to check them out.
Yeah.
Yeah, good stuff.
Cool. Yeah, guys. So I guess, Joe, let's get to the topic at hand that I wanted to discuss. So I wanted to talk a little bit about supernovas with you.
Okay.
So I don't know what even the hell a supernova is. Purposely try to stay away from any definitional stuff so we can just have kind of a organic me being a naive idiot asking naive questions if need be. So I wanted to see, and for the audience, this is relevant because Joe's research is in supernovas.
Right.
And that's I love getting into Marvel comic stuff. So this is like perfect for me because I know nothing about physics. This is supernova, the hero.
Is that actually somebody?
Yeah. Damn it didn't work. I was trying to inject some comic relief, but it has to. You have to know the reference. But.
Yeah, I don't.
Yeah, I don't either.
All right, fine. All right, but
I
supernovas.
liked comics, but
Yeah, Supernova's a
Was it X-Men?
Marvel. No, he's a Marvel superhero.
a standalone.
Yeah.
That's some esoteric.
They're gonna have some movie about him pretty soon.
Oh,
I'm
okay.
excited about it. But anyway, actual supernovae.
Yeah. What are they, Joe? What the hell?
Well, so I mean, I don't know how. Like I said, I don't know how confidently I could speak on this stuff. I recently switched projects, right? From like I was studying massive stars and like dynamics and stuff like that, right? So I was looking more at like, they call it astrometry, right? It's basically using Gaia to make just measurements of like parallax and like how they move on the sky and stuff like that. But after talking with my advisor, it seemed like we should probably switch projects, right? So now we're studying supernova stuff, which are things that he's more comfortable with and he knows a lot more about. I probably on a hierarchy, I am just above a naive idiot, right? So like I could attempt to explain this stuff, but really I'm just coming
hey
to
man,
terms.
that's more than fine. That's better than we are. So we'll take any insights.
Yeah, we're at the ground level right now.
Yeah.
We have no clue.
And maybe we'll also help you out in the future for when you need to
Correct.
give your elevator speech on supernovae.
Sure. Okay. Right. But so a supernova is just basically, as far as I understand, like for the majority of a star's life, it burns hydrogen into helium, right? And that defines on the HR diagram, the Hertzsprung-Russell diagram, where you plot brightness versus temperature. It defines this It defines the main sequence, right?
Okay.
Which is a straight diagonal line, shows a correlation between temperature and brightness.
So it's a linear correlation.
Most of the time they plot it in the log, I think.
Okay.
It's a straight line in the log.
Okay.
Right?
So
But
pretend straight line.
yeah, but so the main sequence is defined when it's burning hydrogen into helium. So most of a star's life, it's on this main sequence. And then towards the end of its life, it starts fusing like heavier elements, right? And it goes off the main sequence and it gets off that well-defined line, right?
Okay.
And at that point, once it fuses through all the heavy elements and goes to iron, right, it can't fuse anymore. So then it will explode, causing what they call a supernova, and it will either turn into a white dwarf or a black hole.
So could you maybe elaborate a little bit on what it means with fusing, though?
Probably not.
Okay, so maybe we kind of just talk around it a little bit ourselves, because I would imagine it's something like we know that stars, they're always producing energy and as a release of heat, right? By basically gravity squishing that inner core so much that it's just getting released as heat energy. Now, I would imagine that the fusing is somehow these heavier elements are being squished together as the fusion process happens and just keeps repeating over and over and over again until you get to higher and higher orders of elements.
Yeah.
You think that sounds probably accurate?
Yeah, that sounds mostly correct.
Okay.
And the reason it stops at iron, I believe, is because you don't net energy by fusion anymore, right? So it's like, I know very little about nuclear physics. That is not my wheelhouse. But as far as I understand, is that once you get to iron, that fusion process doesn't net you any energy, right? So so it has to collapse. Right?
I see. So it has to do with the energy bottoming out in some sense.
Yeah.
Interesting. Exactly. I always wonder. I was like, why always iron does it stop at? But okay, interesting, cool.
Yeah.
So then I guess it's also why all the heavier elements pass like iron. Well, I guess not, because isn't sorry, I keep like stopping my sentences. But isn't gold? Doesn't gold have a higher element composition than iron?
I think so.
Yeah, I think so too. We got to investigate why some of the elements that are higher than iron can actually exist naturally.
Right. It has something to do with the R process, right? I learned very little about this in cosmology, but there is a complicated process that has to do with when the stars die, like how it can create these heavier elements.
I see.
So dramatic. Stars dying, exploding, throwing cosmic tantrums. You know, I always hear about like the cosmic death rays. Mm-hmm. So when do those come in?
What are those, like GRBs?
I guess
gamma ray bursts.
Sure.
Yeah, the gamma ray bursts. Have you ever heard of those, Joe?
Yeah, I've heard of them.
Yeah. But I'm sure you're. I know you're not. That's not your area of research. But
so
I know like higher energy.
So please calm me down, Joe, because I constantly think one day there will just be a beacon of a cosmic ray blast.
That's a good way to go, man. It's
that
quick
glasses our Earth. Yeah, it just glasses our planet. In one instant, just. Whoosh.
It's fine. We'll just be vaporized.
We would see it coming, right?
Yeah, we would feel our burning of our skin.
No,
probably.
sure, but we would see it coming. Please tell me. Please tell me yes.
I think we would feel it actually.
Again,
see it maybe.
I am just totally guessing, but I would think no. I think it would just happen. I'm guessing it would travel at the speed of light, and so it would just.
No, but we got to see it coming. Right?
I think I read something though that it said that we would feel our skin boiling basically first, though. I don't think it would be a quick, painless death. I don't know how accurate it was. I don't even remember the resource, but I remember reading something where it would not be that pleasant as we would expect, because it's like, we already feel the heat from the sun.
Yeah.
And then if something like that high energy is like approaching us, we're still going to have a baking time over some period of time before it actually hits us.
I guess what I'm saying is, do we know what kind of planets or like
what celestial objects actually turns into gamma ray bursts?
No, sir. I don't know. I mean,
I'm just positing a question. I don't know. So are they related to supernova in any way? I don't know.
We've got to be fair, because Joe is new to this area too.
This is the thing about PhDs; they're very specialized in one.
Yeah, exactly.
Thing. You asked me a question about condensed matter. I don't know. I don't know. They asked me about condensed matter. I don't know. I tell them I don't know.
But so
I'm just asking questions here.
Yeah. They're interesting questions, but we may have to like research or something beforehand.
Maybe it's just my anxiety. Like I just drank too much coffee and I'm just overanalyzing this.
It's good though. Good to have energy. So
I don't
keep
know if
that
it's
up.
energy. I'm just like sitting here boiling, like just on the inside.
But yeah, so Joe, the supernova though is like one of the. There's a step before supernova, right? I remember there being something like white dwarfs or something involved.
Well, like I said, after that comes after.
Comes after the supernova.
Yeah.
What's before the supernova then?
That's when it comes off of the main sequence, right? So that's burning hydrogen to helium, and then it goes into heavier elements, and depending on how massive the star is, will affect how that process goes, how fast it is.
But do you remember if there's a name to the star type that comes before it?
I'm not sure I understand the question, right? Like,
because I know there's like a cycle to stars,
right? Like,
so I know they go through like these phases.
Yeah,
and I can't remember exactly what the names are.
Maybe
it's not even important. Or maybe
that's what I was trying to refer to with the main sequence, right? So that's like majority of a star's life, and then that afterwards they just call that post main sequence.
Okay,
stars.
okay,
right.
So just right when it gets off that main sequence, then it turns to a supernova.
Well, not right. Maybe relatively speaking, the process is pretty short, but it could take hundreds, thousands of years for that to happen, depending on the star.
Okay, cool, interesting. So, with your supernova stuff though, is there anything like really interesting that you've been reading about lately?
I mean, not particularly. What my project is we're trying to figure out how stars evolve, right? We actually don't have a good model for how.
And what does that mean, evolve?
How they change over time. Right. So like the main sequence, like I said, is well defined. We know that pretty well. But what happens after the main sequence can be pretty chaotic. And then even what stars go supernova or like what happens to them afterwards, like we don't really know very well. Right. So to do that, you need to get observations. Right. So my project has to do, maybe you could say it's astronomy related, has to do with observations. So basically, you have to see a star to confine this theory, right? You need to see a star before it explodes and then capture it right after it explodes, right?
Good luck.
Right. So it's a pretty coincident, like most of the time those observations just are accidents. Right? Yeah. And those observed by Hubble, I think, are of order 20 historic observations, where something like that has happened, where you see a star and then you happen to know that it went supernova, and then it's out of your camera lens, right?
Now, are you guys using some real heavy astronomy gear, or do you just use?
I'm using Hubble.
Oh, you are using Hubble.
How does this one guy observe all this Hubble guy?
God damn it, Juan. Actually, you know what? I actually saw where Hubble used to do his first astronomy research at
California.
California, yeah, Mount Wilson. It was crazy because my school was like the ones who owned that place. I was like, oh shit, I didn't know that. My old undergraduate institution. And it was cool, man. They had a giant, like 30, I forget what they called it, like 30 something. I forget the measurement, maybe 30 centimeter telescope or something. but it has to do with classifying the lens. But it was a giant telescope that basically you could turn with like a lever and it would move wherever you would point it, and it was cool. They had actually a interferometer there too.
They have Hubble's brain in a vat.
He's actually still controlling it.
Yeah, to this day.
Yeah. But anyways, to finish my project, right. So basically, what we want to do is get more observations of supernovae, right? So either direct observations, or you can get it after the fact, right? There's like supernova remnants, right, which you can get some information from. Like after the star explodes, you'll see like a puffy cloud in the sky for a long time, afterwards. And so to get enough information from those supernova remnants, you have to get more than you just basically need more observations.
So there are different subtypes, right, of supernova?
Yeah, there's type 1 and type 2, and then in those types there's subcategories.
Oh, interesting.
Right. And it depends on complicated stuff dealing with spectrometry.
Like, do you kind of have a type that you guys are looking at right now, or just trying to characterize?
Not particularly.
Okay,
at the moment.
Still kind of figuring out.
Well, we're just trying to get as much data as possible.
In general?
Right.
Nice.
Yeah. So we want to get of order like a few thousand supernova remnants cataloged, and so I'm trying to come up with like an observation technique to like get. So like Hubble can only see so far, right? And then there's a bunch of fuzzy stars in the background that are like so far away that they can't be resolved, and I'm trying to see if there's any way to get information from that like fuzzy background.
So I imagine you do a lot of programming, right?
Yeah,
because like to me this is like a prime example of where it would be beneficial to have like some kind of AI or something. You know what I mean? Some kind of neural network or something where it's just like you don't have to monitor the sky 24/7. You have this like program that scans the sky and then reads certain markers of like telltale signs of like you're saying.
Yeah.
Stuff.
Yeah, I could see what you're saying. I mean, probably that would be useful. But since we're dealing with of order, not many events.
True.
I don't know if that's necessary. Like one of my friends worked on gravitational waves. They did like citizen science stuff, which was kind of interesting. Like for detecting gravitational waves, they just taught a bunch of people that were interested in trying to determine like events. They had like a program for teaching them how to read gravitational waves and categorizing them, and so then that filters through to the scientists. And
do we know anybody at our university that does gravitational wave stuff?
I don't think anyone
does
stuff like that. It's mainly supernova, core collapse supernova, and a couple of cosmologists and one observational guy.
Okay. So Joe, I wanted to ask you, man, a particular question that I was kind of thinking it's fundamental stuff with astronomy.
Sure.
And one thing I was not so certain on was how do we actually measure the distance of stars?
The distance to a star from Earth?
Yeah.
Yeah, I mean that's a great question. It's very difficult, right? That's one of the most important things in like cosmology and stuff like that is determining accurate distances. It depends on how far you want to go, right? There's different techniques for different things. For a majority of the stars that are like nearby, like constellations and stuff like that you can see, they use something called parallax, right? Which is my dad works for an optometrist, right? And that he uses parallax. So it's kind of like an analogy. I could try to explain it. It's like if I look at my hand and I close one of my eyes, right? It looks like it's at some point in my field of view. And then if I close the other eye and open vice versa, it looks like my hand shifts a tiny bit.
Right.
And that's parallax for your eyes. And so imagine doing that with the planet Earth revolving around the sun, or like a satellite revolving around the Earth, right? Like if you treat like the sun as the center, and then you have the Earth on one side, could be analogized to your right eye, and then you revolve around to the other side of the sun, that could be considered opening your left eye. And if you look at the same object, it kind of constrains through that angle how far away that star is.
So I'm a little bit confused about the jumping part, though. What does the jumping indicate?
Well, so the problem is like when you look at a star, right, you have no idea how far away it is, because it could either be the case that it is bright and far away, or dim and close, and you'd have the same brightness.
Yeah.
Right? So you have like a line of possible locations for this star. Mm-hmm. But then if you go to a different location, you've kind of triangulated more or less the position of that star, because you have another intersecting line that defines this point.
Right.
For the potential location of the star.
Yeah, that's cool, man. So then so then your distance from the Earth to the star is a function of how much that object jumps when you switch your view.
Yeah, the angle, right?
Interesting.
So the idea is that like when you have the correct, I guess, distance, the object should not have this parallax, right? It shouldn't have this it shouldn't observe this jumping effect.
You're going to observe it regardless, right?
Yeah.
And then all you do is use something like small angle approximation.
Because I've done this experiment in the lab with a parallax experiment, where it's like you have a pencil and then you have a mirror, and then you kind of move your eye left and right, and then you try to align the image in the mirror to the pencil or something. Mm-hmm. And then, like right when you get the actual, like, how would you say, the distance measured, meaning the real distance of the pencil behind the mirror, depending on the kind of lens it is. Let's just pretend it's producing a real image. So it's saying like your image is 14 centimeters, let's say, in the mirror, and that's how you get the distance. When you observe that the parallax between the two is basically you don't see that.
No, I think it has something to do with like focal distance or something, right?
Right. But I'm saying like you kind of get this mapping of like the focal length of your mirror.
Yeah, but I think that has to do with like you're looking now exactly where the two rays are meeting at that pencil. Yeah, which is different than I think what Joe is saying.
So it is different in your case.
I think it's the same. You're exploiting the same physics, the same idea, but
his is independent of like you have to line it up. It's basically saying that you can look at this planet at any 2 points, and just wherever that jump is, then you have an idea of how much distance you have now.
Gotcha.
Because the actual distance is a function of that jump effect. Whereas yours is like you're actually trying to line it up intentionally to where the two rays are basically exactly equal.
Gotcha.
At that distance.
Yeah.
But okay, cool.
I mean, just to go a little further, I mean, if you want to know distances to further objects, which is really important for cosmology, you could look up something called the cosmic distance ladder, right? So there's like different observations. Like, for instance, one of the most important has to do with supernovae is the Type 1a supernova, right? And that's important because it's like they call it a standardizable candle, I think. It has like a characteristic brightness to its explosion. I think it's due to the Chandrasekhar mass limit. There's like a specific type of
star. A lot of terms I don't know anything about.
There's a specific type of star that its evolution is well known, right? And so basically, it's known to explode at like I forget 1.4 solar masses or something. It's known to explode at this specific mass, right? And so you can predict how bright that explosion should be, right? It's one of the few examples where we know what should happen to the late stage life cycles of these stars. So because you know how bright that output should be, you can get good distance measurements.
Okay.
And so that's important because, in cosmology, finding distances to faraway things lets you determine the past of the universe, helps you figure out like how old the universe is, when it should end, stuff like that.
Interesting, man. Very interesting.
The speed of light is constant. Right?
Huh? Sorry, I missed that.
I just said the speed of light is constant, so distance over time.
Oh yeah.
Yeah.
Thank you,
Juan. Easy peasy, man. Easy peasy. At that point, it's easy.
Yeah. Cool, man. That's cool. Another one I wanted to ask you, Joe. Fundamentals. Let's get back to the basics here.
Sure.
I wanted to ask you another one that I kind of know the idea too, but I just want to see what you also have to say about it. So how do we determine the chemical compositions of celestial objects?
Spectroscopy would be my answer, right? So if you want me to explain it, that's kind of long-winded, but
just as simply as you can. You don't have to get too crazy with it.
I don't know how to explain it simply, right? Because it requires quantum mechanics and basic understanding of quantum mechanics.
So let me maybe give it a shot, and then you can maybe fill in the blanks.
Yep.
So what I would say is spectroscopy. Basically, what I would imagine. I actually don't even know really with astronomy. I would imagine what you guys do is you point some kind of telescope or something at a, let's say, a planet or something, right?
Yep.
And then what happens is that planet is going to be radiating certain light.
Yep.
That I guess it's going to get that light from bouncing off like a sun or something or another star. Is that true? Maybe that's wrong. Maybe I should just continue to go. I'll just say it's going to radiate some kind of light.
Yeah.
Then that light is going to get collected by the telescope.
Yep.
And when you actually look at what the light composition is, you're going to get different frequencies of light.
Yep.
Yeah.
And then those different frequencies of light indicate how much certain chemicals your planet should be made up of, because there will be different absorptions of those lights.
Yep.
E equals HV.
Well, it'd probably be
Okay.
it'd be emission, right? In the example you're talking about, there's emission and absorption.
It'd be emission.
Yeah,
because you're getting the light emitted.
Oh, because the light is coming in.
Right.
Yeah. My bad. Okay, so how much of the light is emitted in those different frequencies?
Right, and the reason you need to know quantum mechanics is because the only way you could tell what those elements are from those energies or those frequencies is because there's only specific energy levels allotted to different elements.
Right. Yeah. So you really got to know your quantum foundational stuff, or at least you needed some kind of reference chart.
Yeah.
Unless you're just some kind of crazy Sherlock Holmes who knows all those values.
Yeah, you remember.
But okay, but then the next question I have is, there's got to be some weird coincidences where you have certain elements that actually radiate the same kind of energies, or radiate the same, emit the same values of energy, yet they are two different elements. Is that true or no?
So
I don't think so.
So you're talking about like degeneracies of like, if you have a peak, that corresponds to some frequency, how do you know what element it is?
Yeah, especially if there's repeats somehow.
Yeah, I mean, it can be a little fuzzy. Like when you look at the profiles of in reality, when you look at the the spectrum or the wavelengths of the different emission patterns, it can be difficult to determine what a specific element is. Sometimes it's well defined. Sometimes it's like, oh, it could be this or that. But most of the time, you can accurately determine the element.
Yeah, because if it's anything analogous to like spectroscopy in the condensed matter, it's kind of like they have the same thing where you will, depending on the type of material, you can get peak broadening, and then that you can't really tell, or your degree of accuracy for measuring like what frequency is there. It's kind of like, well, there's a big error bar, but there are some, I guess, depending on your experimental parameters, right? In your case, for astrophysics or something, like you're trying to gauge. It depends on like how good, I imagine, the data collection part is, depending on all that. So like, yeah, I think I don't think we see degeneracies as much, because I think the orbitals, the way, well, not the orbitals, I guess, because we're thinking about planets. I'm thinking about condensed matter. But I imagine it's sort of analogous. Like you only get certain configurations for energies because the orbitals are unique, and to certain elements.
Yeah. Yeah, it goes back to quantum mechanics.
Yeah. I forgot you did this stuff too, Juan.
Yeah. Little spectroscopy.
I was like, oh shit, I forgot Juan actually did spectroscopy stuff. I remember a long time ago when you were in the lab. Back when we were, just coming in here, and you were doing your little spectroscopy shit, and there's something went wrong with it.
Oh yeah,
I remember.
I messed it up one time. I did something really stupid. I'm not going to say what it is. I'm not going to incriminate myself. I plead the fifth.
Yeah.
But yeah, it's cool stuff though, because I always wondered that as a kid too, like how, you look at the star and then you see a color.
Yeah.
And you're like, well, how? For me at least, I was like, how does that happen? How does that? Like, why could I see that? Like, for instance, like I always wondered, why is Mars red? I'm not a planet guy, so this might be a stupid question. I know that's the color of the soil.
Yeah.
But
why?
Elements.
Why red?
I know that elements. It all comes down to like the chemical elements and the kind of colors they give. But I don't know.
Yeah.
Why, does anybody have an answer?
Why
for
is
this?
Mars red? No, Joe.
Is it go
It's
back?
a great question to me.
Does it go back to Greek time when it's like it's a god of war? It's angry. Just
As soon as the Greeks said it was a god of war, then Mars turned red.
Well, I mean, I don't know.
It has to go back to the chemical stuff.
Specifically speaking about Mars, I mean, it might be for the same reason, but about stars, I mean, we already talked about it. It's because of spectroscopy, right? Because different elements have different wavelengths of light.
Yeah, exactly.
Different wavelengths of light have different colors, right?
Yeah.
It might be.
But in this case, it would be absorption, right? Because the sun we're getting the light from, meaning that the Earth or the soil it's absorbing red.
Well, it's reflecting because when you have colors, like everything is colored because the light, it actually absorbs all the other colors and reflects back what it is, right? So the sun is reflecting the red light from that soil.
Right. So in this case, it would be absorption then, right? Like we're getting. It's not even because in the example of Joe's, the light is being emitted from the sun.
Oh right.
So this would be absorption, I guess.
I don't know.
Maybe. I mean, normally the example I see for absorption is like, say you have a star behind a cloud of gas, right? If you have something hot, the gas is going to absorb, everything but its composites, right? In the example of Mars, I'm not sure. Can it be considered absorption? Maybe.
It depends on what you're talking about.
He's not a fan. He's not a fan of Mars. You heard it here first. What's your favorite planet in the solar system, dude?
Never been asked that question.
You one of these Pluto guys? Pluto is a planet. You like, what's his name? Neil deGrasse Tyson. Yeah. He's constantly trying to ride off Mars.
Yeah.
I mean,
Pluto.
I don't know. Maybe it's a cop out, but I'd just take Earth, right?
Earth?
Yeah.
Oh. I was hoping you'd say something like Venus or. No, Venus is not that cool. Saturn. I love the gaseous giants because they're the most interesting to me.
Saturn's kind of the plebe tier planet, though.
I think so.
Yeah, because it's got rings. Ooh, I'm so cool and special. I got rings.
That's what makes it cool, man. It's a champion. It's a winner. It's got rings. It's the Michael Jordan of our solar system.
I love those images of Jupiter, right? I have them for my backgrounds.
Jupiter is beautiful, yeah.
Yeah.
From the Juno missions. NASA has some really beautiful images of Jupiter.
Mm-hmm.
Do you think there's a Planet X? I'm gonna get into conspiracy theories. I'm kidding.
Gotta get Eddie Bravo on the podcast.
Yeah, get in those conspiracy people to come in.
Planet Nibiru.
Dude, and this is why I love Brian Cox, because he used to, when he was on Twitter early on, he would just shit on everybody, every conspiracy guy, because they would come at him and ask him is Planet Nibiru real or whatever, Planet X, and he was just like, you can shove that planet up your ass or whatever. I don't know his. I'm sorry if I butchered if I gave you a weird accent, but
is Brian Cox British?
Yeah,
I think he is, or
yeah,
something like that. Yeah.
It's. I haven't heard him in a minute, so I'd have to.
He's got a really soft, soothing voice, though. That's all I know.
Yeah, I can't do it. I don't want to do it. But yeah, basically,
he's going to devolve into Trump.
Yeah,
I already see it right now.
I know. Yeah.
My name is Brian Cox. I'm an astronomer.
Yeah, I know a lot about supernova.
Wait, is Brian Cox an astronomer?
He's astrophysics.
Okay.
Yeah.
Is that confirm that, Joe?
He might be a cosmologist.
Oh, I
think he works on high energy. I thought he worked.
I thought high energy as well. For some reason.
I thought he worked with like particle stuff.
I think LHC.
He did work at LHC, but I remember him saying he switched.
Oh,
or something.
Well, let's just not say what he is then for now.
Brian,
can you confirm?
Come on the show.
damn! If we get Brian Cox on the show, we made it officially.
Yeah, he wouldn't enjoy his time.
No, he would.
We're too goofy. We're too goofy. We're. But he
He'd
likes
be like,
singing
wow,
around.
so there are retarded physicists out there.
I'm gonna have to beep this. What time is this? 41. All right.
Oh yeah, I'm sorry, I can't say the R word anymore.
Sorry. Retarded potentials.
Okay, you saved yourself with that one.
That's what I meant.
Yeah, that's the quote unquote. That's actually was going to be the name of the show instead of Eigenbros, but I decided against it.
Retarded potential.
That would have been really good.
Maybe we can use that for something else.
Yeah. But what was I going to say?
Do that for your problem solving series.
Yeah.
True. That's actually a great idea.
Mm-hmm.
No, but yeah, there's a lot of things I ponder about the universe. You know, like the.
It's not a bowl.
Like what is dark matter?
Oh God.
Well,
Joe's like, God damn it.
Well, that's the question, right? Like, if I knew the answer to that,
That's literally the question.
Joe, you have a Nobel Prize answer waiting for me.
Right.
No, what's like the? No, you know what? Let's not talk about that. Let's talk about black holes because I know you did this like really cool thing, and you like the time that they discovered or they took the image of the black hole.
Yep.
You kind of did this like calculation.
Yep.
Like
for social media. Yep.
Yeah, for it was a really cool calculation because you showed, if I remember correctly, like the pixel.
Yep.
The size that you would need of the pixels to get a good resolution of the image.
Something like that. Yeah. It was basically the resolution you would need to resolve the recent black hole image.
Yeah.
In 1 pixel, and it was like twice the diameter of the Earth.
Damn.
Right. And they do that through radio interferometry, right? They have telescopes all over the Earth.
Yeah.
And so they basically turn the whole planet into a telescope, more or less.
Insane.
Yeah.
But yeah, I mean, the calculation was fun. I mean, it's really basic. It was just, I mean, to a layman, maybe not, but I just derived the Schwarzschild radius, right?
Casually. Back of a napkin, I casually.
I could do it right here in 2 seconds. It's just, well, you know, light gets sucked into a black hole, right? So you just say the kinetic energy is equal to the gravitational potential, and then you solve for R. And, and for V, you plug in the speed of light, and that's it.
True.
Cool.
So it takes 2 seconds. But and then use small angle approximation, and then I pull the data from their paper for the frequencies that they probed.
Sweet.
And then you could find the diameter of the telescope that you need to figure out the to resolve the.
So
black
that's
hole
basically how they did it. So you basically figured out how that would have been a paper for you, nature. Just figuring out the diameter you needed for that image. Right?
Yeah, if I did it, maybe years before they started, yeah.
Yeah, see, they just got lucky that you didn't think of it first.
Yeah, exactly. Would have swept that up.
I always like to frame it that way. Like, if I have an idea and I go back into, like, the research and I'm like, oh, I had this idea. This could have easily been my paper.
Just send me back in time to Newton.
Yeah.
I'll discover all of physics for you.
It makes me feel better, because suffering from imposter syndrome in grad school is very real. So
yeah, true that.
But
also suffering from delusions as well.
That's grand delusions.
Delusions of grandeur.
Yeah, which is, I'm sure, part of the...
I'm sure of many physicists. I've heard this too many times that they think that they could do all... They're like, oh, this is all low-hanging fruit. You've even said this.
I've said that.
Yeah.
I agree.
And that's why I just look and I'm like, no.
No,
you forget all the context of history.
Yeah, true. I am being tongue-in-cheek for sure.
Yeah, we still don't know shit.
Yeah.
So...
I have some self-awareness.
I know. I just got to bust your balls, Juan.
True. Okay, hold on. Actually, my eye fell out.
Yeah, I was noticing that. I was like, is Juan playing with a lens or what is that? So Juan is going to readjust his contact lens. So me and Joe will continue on without him for now.
Okay.
So Joe, I want to, let's see, can we think of any more interesting fundamental questions? So I kind of want to give some fundamental stuff just for my own,
Sure.
or some fundamental questions for my own satisfaction as well as the audience, because, we always talk about other physics, but never astronomy. So I kind of want to just get my foundations of astronomy straight here.
Okay.
So you did mention that you don't use GR or general relativity that much in astronomy.
Yeah.
But
in my experience.
Okay. Actually, let me not ask that then, since you don't use it in your everyday. But what? So then, I guess a question would be then, what kind of math do you use normally? Do you even have to use calculus that often?
Calculus, sure, right?
Okay,
I mean,
pretty much if you're in physics, you're going to be using calculus, right?
Right. The main thing I've been learning that I wasn't really taught this is like stat stuff, like Bayesian inference.
That's kind of what I was thinking, and that's a little bit where I was kind of heading, because I'm like, it seems like it'd be a really useful thing for you guys to learn probability. Yeah. And I feel like that in a lot of areas of physics, especially experimental stuff. Yeah.
It's kind of interesting. It's like a hidden secret math world that they don't teach you until you actually like are on the job.
Yeah, and I don't get why.
Right.
It seems so useful.
Maybe because it's just like a little more like conceptually dense than like. So there's two types of like statistics, like two philosophies, I guess you could say. Mm-hmm. There's frequentist, and then there's Bayesian inference, right? So frequentist just means like what you were taught in like middle school or whatever. Like if you want to find the average, you take the number of events and you divide by the total or whatever. But for like Bayesian inference, it requires you to basically say your prior, which means like if this is my model of like the universe or whatever, I expect this event to happen this percent of the time, right? And so then you do some observation, and then it either supports or maybe it comes in conflict with that model.
Right.
So,
and I guess I got for the big takeaway of Bayesian stuff is you're basically adding in constraints into your probability equation so that you get a stronger probability that actually correlates with reality.
Yeah, I think you could say that, right?
Yeah.
So, I mean, the important thing is just like it helps you acknowledge your own biases.
Yeah.
Is the main, I think, strength of it.
Right. And it adds a realness to the calculation as well.
Yeah.
Like we say, oh, you could flip a coin heads or tails 50% of the time. It should always come up 50%, but it's like in real life, there's also weight to a coin, right?
Yeah.
The side with George Washington's head has some weight to it, so maybe you can add a constraint of weightedness on there, and then
that's true. Yeah.
You're adding constraints to make it so maybe it's actually 49% and 51%, or something like that.
Yeah.
So cool.
Totally.
How's your eye?
What did y'all talk about?
We were talking about math
about stats
that you use in, or I guess for astronomy, and we were kind of saying how probability is one of these ones that I kind of think is really. It kind of doesn't get its due, I feel like, in physics. Like, we don't go over much probability stuff.
No,
yeah.
It's very, very touch and go, if anything. It's like only like what? Maybe some things in quantum have probability with it.
Bro, they don't want you to get any ideas. They don't want you to know that becoming a statistician pays more.
They're trying to keep us retained in the system as long as possible, huh?
They are.
Actually, I really love statistics. It's like one of my favorite subjects.
Yeah.
Like I took it in undergrad for like a math minor kind of thing. And stats is just awesome, right? Like I saw some Twitter thread or something where they're asking like what's like some magic that basically happens in math or science that it's like you don't understand it but you still don't like believe it. Someone said the central limit theorem in statistics, and I would agree with that, right?
What is that?
Central limit theorem is basically like you have a random distribution, you have a certain number of events, you're always going to get a Gaussian. Right?
Oh, yeah.
The fact that you get that normal curve, they call
every time.
Yeah, normal is bizarre to me, right?
Yeah.
The fact that happens seems like a deep fundamental mystery to me, and
it's one of these things that you're just like, holy shit, like,
how
have I just only learned about this in life?
It's really
you're
crazy.
like, wow, this just tells you so much about how the world is.
Yeah, it's basically like how order comes out of chaos, right?
Yeah,
and it's just like how that even happens is
right.
Crazy. And like I was watching this Netflix series, I mean, I'll plug it, I guess, is Connected. I don't know if you've heard of it, but
no.
anyways, it tries to explore how like the world, how we're connected to like everything in really surprising ways. And
Is it a hippie or a science show?
It's a science show.
Okay.
So they did an episode on this.
Terence was worried this was going to be that show with the quantum spookiness.
Yeah.
Call it that fake
What the
scientist.
bleep?
What the bleep? Do we
Yeah,
know?
what the bleep?
No, it's not like that.
Yeah, I don't need another one of those.
Yeah.
But they did an episode on something called Benford's Law. I'd never heard of this, but apparently it's known in like the stats community and stuff in math circles. It's basically how like if you pull any set of digits, it seems like the connections are everywhere. It's like if you pull a set of digits from like they pulled it like from example like in astronomy like data table log or whatever, and for like doing multiplication tables basically, they pulled like all these digits, and if you keep the first digit, what would you expect the distribution to be of 1 through 9, right? My first guess would be like something uniform, right? It would be equally weighted across all of them, but that's not true. Apparently 1 shows up 30% of the time, 2 shows up like a specific number, and it actually looks like it falls off as like 1 over r or something. Right? So like 9 shows up the least.
I don't like that.
Right. It's crazy.
I don't like that one bit.
What was the justification behind that?
There is no justification. It's just like everyone, even the mathematicians that they interviewed, were like, yeah, it's crazy. I don't know. And it's just like they see it. They use it to help determine tax fraud, to figure out whether you doctored an image. Because
I've heard of that, yeah.
So it's basically like if you somehow pulled these random digits out of these situations and it doesn't follow this law, then
something's fishy probably.
Right.
I've heard of that because I was like, I always wondered how the IRS is so good at detecting tax fraud. It's because of those, like you said, these magical math mysteries that nobody even realizes. But
someone
these
did it
genius mathematicians figure this out, and then it's like, gotcha.
Someone did it with Enron, right? Basically, like after the fact, saw how they cooked their books and how it basically deviated away from this law. And so it's
amazing.
So, pro tip: if you're going to be shady business, hire some mathematicians to cook your books.
Yeah.
Shocking.
Interesting. What was that thing called again?
It's called Connected.
Connected. Interesting.
Right. It's on Netflix. It's because I listened to this podcast called it's by NPR, right? It's basically WNYC, right? Radio Lab.
Gotcha. Yeah, Radio Lab. Yeah.
Right. So one of the researchers on that show made that Connected.
Nice.
So
NPR has good content.
Yeah. I used to listen to NPR.
Ira Glass and what's the other guy's name?
Like this.
Yeah.
Hello, everybody. That's the original ASMR.
Yeah.
Just trying to calm you down. Here are
So
the
true.
news for today. Please remain calm.
Yeah.
Yeah. I used to love NPR. It was so good.
Me too. I used to listen to it all the time. But then finally the begging for donations got to me.
Wait, they have an NPR station here? They do, right?
They do. They always do.
Yeah.
But there's always that time of the year where they just start asking for money constantly, and I'm just like, I
Hey
can't
man,
take it.
it's like Wikipedia, bro. I don't.
I know, but I'm a selfish bastard, and I'm just like, I can't deal with you
I give
asking
them
for
at
money
least
all the time.
literally for a cup of coffee. I give them that. I'm just like, here you go, folks.
Yeah. But I wish you could just donate and then just never have to hear the asking for donations
Become
again.
a lifetime member, Terence, and you will never have to hear a word from us again.
I guess we should take notes for that for the Patreon.
Yeah, that's what I'm saying.
Yeah. Pass through the listeners. Watch your count literally go like that graph where it's like 1, 2, and 3. 9 is the least. That's insane, man. So is numerology real?
So what you're saying is numerology is real. Just like some idiot who gets nothing out of nothing out of the take.
Yeah. That's.
I guess the exact wrong conclusion.
Yeah. So you're telling me numbers don't lie? No, but there is some. But isn't that what mathematicians are basically? Numerologists. Come on, that's one. Think about it.
It's funny, like when you're a kid, when someone says like you're a mathematician, then you think, well, what does a mathematician do? I guess they just multiply really, really big numbers. You know, like when you were a kid, did you actually know what a mathematician did?
No, never.
Yeah,
never. I didn't. I didn't
guess
even
they
understand.
just add a lot of big stuff, big
yeah.
numbers and stuff.
Yeah, it's just. I mean, it's fascinating once you get to that level. I think when people, I was going to ask you like, what if somebody wants to do astrophysics, because we have physics students listening, and if they want to go to grad school, like, if they want to study astrophysics, like, what would you recommend brushing up on? Like, none of this numerology stuff, obviously. No, I'm just kidding. But like, do you think it's beneficial to take a stats class or something, or like stuff like that?
Well, yeah. I mean, are you talking? So you're saying like at the undergrad level, like recommendations for like?
Yeah, because at grad school, I think most of us are kind of like, we're not really going to study. We're going to study one or two things that we like, and then call it a day.
Yeah, usually when I was an undergraduate, I like to get like tips for like things of how I can differentiate myself.
Yeah.
Like, what are some good tips you can differentiate yourself from the herd?
Well, for that specifically, I would say coding. Actually, that's probably maybe my biggest hurdle, is trying to teach myself how to code.
Yeah, people don't realize this, but physicists, it's not required for us to take coding classes all the time. Depending on the school, but I think it's pretty. I've seen it widely enough where a lot of physicists don't know coding, right? They're just learning it now when they're getting into graduate school, even, or maybe a little bit in undergraduate. But coding I think is a great tip.
Yeah, you learn it on the streets, right? As a physicist,
exactly.
Right. So you might pick up some bad habits left over from people who just taught themselves how to do stuff, right? So, like, I think my workflow would be, exponentially faster if I just knew how to code like a whiz, right? So,
and you recommended languages for astronomy?
Let me add this, because I was looking into this because even me I plan to be an industrial physicist, so they do require coding of some sort, like C+ or something. Now, the best way to do
C++.
C++, thank you. Yeah, C+ is
That's not your grade.
Yeah. Like, a lot of community colleges offer certification programs for this. Like, it's like a summer term for you to just be certified in this, and that's usually enough to get you in the door in a lot of places, because it shows that you actually know it. Like, you can write in your resume that you know C++, but it's not going to help you, or Python, but it's going to be pretty much hearsay.
Yeah, they'll test you on it. Like, they'll give you a code block or something and say, what does this do, or what's the problem with this code.
So
every time I do computer science interviews, I'm like, shit, I really don't know shit about computer science, I guess.
So that's what I mean. Like, I think look at your community colleges. Typically your universities will not offer these certification programs, like technical community colleges will. Like, they'll just give you, like, because they give out associates, right? They pretty much like handle short-term kind of like certification programs.
Yeah, useful thing I never did when I was undergraduate that might help is actually look for like astronomy related jobs. Like, if you really want to go into astronomy, look for actual astronomy jobs on like Indeed or Monster, or what are some of the other good ones?
For museums and stuff. What do you mean? I'm genuinely asking.
Working for museums.
Yeah, because museums have like planetariums and stuff.
I don't want to consider it an astronomy job. I would consider an astronomy job like actually working in a
like
national
observer?
In like a observatory or something.
Gotcha.
So look for those jobs and then see what skills they want from you, and then they'll have a list of things. Usually they'll say like, oh, you need a PhD in ASTRO, 3 years of coding in whatever the fuck the good language is for that time or whatever.
Spanish. Coding in Spanish, El Planetario is.
But so that's a good way to see what you should need as well.
Yeah, I mean, for the most part, anything in Astro is going to need coding, right? Like, even if you're in an observation, right? Most of the time, you're not actually sitting there looking through a telescopic lens, right? You're telling the telescope where to look with a computer. The only rare exception to that is like some people I know who fabricate like the instruments, who like actually machine like the telescope parts and stuff like that. But like everything else, I think you're going to need to know how to code. So.
And that's such a universally useful skill anyway. So let's say you are sick of Astro by the time you get to grad school or something and you want to just quit and go somewhere else. Coding, that sticks with you for pretty much any tech-related field, right?
Yeah.
Useful in every single field.
So, Joe, you as a physicist, do you think if society collapsed, would you be able to make your own telescope?
Oh.
No. Answering honestly.
You know the fundamental pieces though that you need, right?
The main problem is like the optics with like the lens and stuff.
Right.
I don't know how you would get the specific
I bet you could do it.
curvature or whatever.
I believe in you.
Because remember, Galileo made this back in like
16.
I think it's 1600s, I want to say.
Right. Yeah.
Sure, I guess. Give me a few years to devote to figure out this stupid lens, and then maybe.
You just gotta polish it real nice, and you know.
Yeah, you become. Because a lot of those guys, they kind of like Galileo. I guess they got really good at I guess making glass, right? Or glass, technically.
Yeah, glass for the lenses. Yeah. Or maybe they just hired some guy to do it. They're like, you know, to do this. You make this glass for me.
Yeah, true. I'm
Because they were all rich. Remember.
Yeah.
Those guys all had money.
But all it really takes is, I guess, if you wanted to make a telescope at home, you technically could, right? If you had I think you could make furnace.
I think you could make a telescope fairly simply.
Yeah.
I'd have to remember my optics, but I think if I drew a few ray diagrams, I could probably back engineer it.
True.
Well, yeah. And then one other thing would be like the coordinate system, right? They use.
What do you mean?
For telescopes, they use RA and DEC for determining position on the sky. So you need to have some type of like fine motor control.
Gotcha.
Which would be maybe difficult.
Yeah, that might be a little bit more challenging, but I think I think you probably figured it out.
Yeah, because like astronomers back then were more like circumnavigators, right? They used the stars to circumnavigate the world.
Sure.
Right.
Yeah. Well, I mean,
That
it's the oldest science, right? Yeah, that's what they used it for.
You would be one of those guys. You'd be on a ship whether you like it or not, Joe. Yeah. No, it's super interesting, but
I think we're approaching.
I know.
the time.
I had another question though, but I totally forgot.
I think we should wrap it up.
Yeah, sure.
But So, Joe, any final thoughts?
No. I mean, just thanks for having me on again. I guess this secures my place as most common guest. I don't know.
True. Yeah,
I think it is.
True, yeah.
Yeah,
I think so.
I think Joe is the number one.
Yeah, for sure. Number one.
Yeah.
But yeah, I guess if you want to plug anything, Joe, go ahead.
Sure. Yeah.
We can do it at the end, the outro.
Oh, sure. I guess.
Yeah. Stick around for the outro, folks.
Okay.
Thanks, guys, for sticking around and watching the podcast.
Yes.
Just to let you guys know, once again, like, share, comment, subscribe. Follow us on Eigenbros.com, Eigenbros on Twitter, Eigenbros on Instagram, Eigenbros2 on TikTok, and then also follow Joe. Joe, you are Beyond the Physics,
on
or what's
Spotify?
the Twitter?
Well, Beyond the Physics first, of course, guys, on Spotify, Google Play, iHeartRadio.
Yeah, Apple Podcasts, so on.
All those places. You can find them pretty much anywhere. And then, what was the Twitters, Joe, and the socials?
Beyond_physics.
Okay. And then you guys also do Facebook, right?
Yeah, we have a Facebook, right?
Okay.
Yeah, go check that out.
Do you remember the name of it?
Yeah, the page is just Beyond the Physics.
Okay.
Yeah. Verified.
Yeah. No.
Well, you guys are verified, right?
I don't know.
No, I don't think so. I think
Does
it's
Facebook even have those check?
Yeah, I think they do.
I'm sure they had to copy off of.
Well, then I
everybody
guess
else.
not.
I'll have to call Zuckerberg. I know his number.
But anyways, yeah, I would appreciate if you guys go check it out.
Yeah, for sure.
Yeah.
Let us know what you think.
Yeah, actually, let me just add that Terence and I did episodes on that too. So if you really want to hear about our personal lives,
Yeah, if you're new fan to Eigenbros, right?
if you want to dox us, that's how you would do it.
Shit. Well, don't be giving the crazy ass people any ideas.
No, but in all seriousness, please check them out and stay tuned for more, I guess.
Yes, we will see you guys next week.